items. As far as lab this week, we have classification of matter. I'll scroll up, I'll even move this one up in case it's a better view for some people. Remember, you must have your procedure sufficient to conduct the experiment. I have the page numbers there for your lab manual. And you have to have the pre-lab assignment questions attempted. You actually have to try to answer them. They don't have to be correct. You can have a whole week until the lab report's due, which means you can always change your answers. We don't have a quiz on Fridays, and this Friday is no different just because there's an exam. Does not mean there's not a quiz, but since you're going to be having that stressful exam on Thursday, I have the quizzes after exams be group quizzes. The way I run group quizzes is 4 people per quiz page. You do not have to be in the same discussion. Any 4 people is fine. Everybody has to have their name on it. Everybody gets a copy back. So it doesn't matter if it's in the same discussion or not. One person will get the original, the color copy, and others will get photocopies. So everybody will get that back so you don't have to find the person you took the quiz with to see how you did it on the quiz. But the group gets to talk to each other, and it's meant to be fun. You don't have to have 4 people in your group. You can take the quiz by yourself. I do write them anticipating there's 4 brains, plus all the other brains, so they can be a little more difficult than a regular quiz. The exam, you know, is Thursday. Remember, it is sections 1.1 through 3.6. I did put some lecture activity problems up there for what we're going to do today, along with some Little Exam 1 homework problems. Since the Little Exam 1 homework isn't due until October 3rd, I am anticipating that numbers 1 through 100 will be complete. It goes to the end of chapter 3, and I'll see how we couldn't be done in chapter 3 by now. Any questions? We good? Ready to go? Hopefully that helped having that on the screen for you guys over there. I did talk to Fast Food Services this morning, and they're waiting for technicians to come to remove that projector so it can get shipped off to be repaired. So it's not going to be fixed anytime soon, unfortunately. We did leave off after talking about our mass spectrum and average atomic mass and our mass spectrometer. We're going to section 3.2 and 3.3 now. Hopefully, still a bit of review, and then mass spectrometer probably was a review. On the header, the top page 72 is Avogadro does our molar mass as an element and molecular mass in these sections. So as far as review, we want to use macroscopic masses. We don't want to deal with the masses of atoms and molecules. We need to be able to deal with samples that we can touch and feel and not taste. He didn't hear that. So we want a usable mass for our elements. They're reminding us of the definition for atomic mass unit. Remember, an AMU is equal to 1/12 the mass of a carbon-12 atom. And that ended up giving us that 1 atom of carbon-12 had a mass of exactly 12 AMU. I say the word exactly, they put a bunch of zeros behind it as well, because if you're worried about safety, these kind of numbers don't change the same thing. So either you can put a bunch of zeros, or you can just remember its exact number for counting particles and it's per the definition. If we want to express this in units of grams, that's a usable unit, right? Instead of AMU, recall from before last week, we had brought up that the mass of a carbon-12 atom was 2 times 10 to the negative 23rd grams. Ooh, that's a bad 3. That's a little bit better. That really doesn't help. It's a useful unit, but it's such a small amount that we really still can't use that or balance it. Obviously cannot measure that out. So what number of atoms do we have to have a usable mass? They're having us think about 12 grams of carbon. That's something you can put in your hands and feel it with your gloves on and touch it. So let's see how many atoms that would be. If we have 12 grams of our carbon-12 and we use this right here as basically a conversion factor, meaning 1 atom of carbon-12 has a mass of 2 times 10 to the negative 23rd grams. This will tell us how many atoms we would need. 6 times 10 to the 23rd carbon-12 atoms. Does that actually help? We have exchanged explicitly not the author of this thing. The author of this thing rounded the mass of the carbon-12 to one digit in front of the exponential part. It is 2 point something something something. So that would end up giving us 6 point something something something. And I think I forgot to put my stuff. That's the right place for this slide. So many people said Avogadro's number, which you may recall is 6.022 times 10 to the 23rd. As far as a number, I like to add things. Because it doesn't have to be atoms. It could be molecules. It could be pennies, if you want that. Nobody in the world has any pennies. You could be the richest person in the world. You could put elephants, but nobody would live on Earth because there'd be too many elephants. They could crush us all. So it's just things. It's a number that, it's a magic number that means something else, like, what does 12 mean? A dozen, right? Or a duet is 2, or a trio is 3. This is just our chemistry bundle for, as you already know, a mole. 1 mole contains 6.0, I've got my E on, 022 times 10 to the 23rd of whatever you're thinking about. So again, I like to put my things there. We took this huge number that's hard to comprehend and bundled it into a much easier number to understand. 1. Any questions before we go through that table on page? If you can't see something, anybody, but especially you guys, please make sure to say something. So the table at the bottom is hopefully going to be simple. For carbon-12, if we know that we have exactly 1 mole of the carbon-12, we therefore know what the mass is and what the number of atoms is. 1 atom of carbon-12 is 12 AMU. Well, a mole of carbon-12 is exactly 12 grams. Remember I said the only reason why we didn't get Avogadro's number here is because that number was rounded. So if we know that we have 6.022 times 10 to the 23rd hydrogen atoms, how many moles do we have? 1. That's the definition of a mole. So for our hydrogen rope, we would have 1 mole. What would the mass be though? Would it be 1 AMU? Ever? No? Good. They don't tell us hydrogen 1. So we have to think about the mixture of the different isotopes and their relative abundances, meaning we need to use our average atomic mass, or in this case, our molar mass, the mass for 1 mole of generic hydrogen, not specific to an isotope. How would we find out how much lead we have besides the mass given? If you're just given a mass for something and you're thinking about moles, the first thing you probably do is go to the periodic table. Well, let's go find lead. Where are you? Number 82. Well, look at that. The number underneath it is 207.20. That's 207.2. So since the number basically matches except for a 0, we know that that is representing 1 mole of lead, and therefore we have 6.022 times 10 to the 23rd atoms. If we know that 1 mole of a particular element weighs 4 grams, what element is that? What was that? Helium. Helium, good. Or you go to the periodic table and find out which one has a mass noted of 4 grams, or something really close to that. And therefore we also know how many atoms we have. Any questions? So the mole is referred to lots of times as a quantitative bridge between the particle world and the macroscopic world. You know how many particles there are, this huge number, but we can relate that now to macroscopic masses that we can touch and feel and not taste. So we're going to just make sure we're understanding for our carbon and oxygen what the mass will be for a mole of that, and then we're going to do a little practice with, we can see hopefully those masses for our second 2 rows are not going to be the same as the masses in the first 2 rows. So to find the mass of carbon for 1 mole, you just go to the periodic table. Before it was AMUs, now it's just grams for that 1 mole. So the molar mass, the mass of 1 mole of carbon, is 12.01 grams for each mole. What number should be there for oxygen? 16 or 15.99 something, depending what periodic table you're looking at. They are slightly different, meaning once we start doing this type of So let's do these second two. It hopefully makes sense. If we have 10 grams of carbon, we do not have a mole of carbon. Because the mole has a mass of 12.01 grams, meaning we have less than a mole. We'll need to figure out. So for our carbon, to find out how many moles and how many atoms we have to start with our given 10 grams. We're going to use our molar mass as the conversion factor. For every 1 mole, we have 12.01 grams. Doing the math, this would tell us how many moles we have. Our grams cancel out. We have moles of carbon, 0.833 moles of carbon. To find out how many atoms there are, we would use Avogadro's number. We know there are 6.022 times 10 to the 23rd carbon atoms for every 1 mole of carbon. I think I might not have started over so far, so I'm going to have to extend it underneath so I don't get sloppy. And this would give us 5.02 times 10 to the 23rd carbon atoms. Yeah, look close to the bottom there. I forgot I zoomed it in. Any questions about that? It's going to be the exact same process for the oxygen, it's just we're going to have a different number to use besides the 12.01. We'll be using 16. I'm going to shove that up so we keep our carbon kind of in place. So for our oxygen, we're starting with the same mass, 10 grams. We know every mole has a mass of 16 grams. Therefore, we will find our moles to be 0.625. Why is it less than the moles of carbon? It's good to understand why your number changed. Okay.
Divided over a larger mass.
Okay, the masses are different. Is that what's going on here? So the mass of an oxygen atom is heavier than the mass of a carbon atom, or the mass of a mole of oxygen is greater than the mass of a mole of carbon, or some people are more mathematically minded. I'm dividing by bare numbers, but it's good to make that chemistry connection as well. If we want to go to the number of oxygen atoms, we're still using Avogadro's number. That does not change. That's independent of what the things is. It's always 6.022 times 10 to the 23rd, in this case oxygen atoms, for 1 mole of oxygen, just like the number 12 always means a dozen. It doesn't matter if it's eggs or pencils or elephants. This would give us then 3.76 times 10 to the 23rd oxygen atoms. So I was going to be able to squeeze that one in. Any questions? Oh, this is a really sloppy three. Thank you for saying something up there. I saw that edge coming in. I was trying to squeeze. So, now don't be afraid to say something. If you need to consider making carbon monoxide, CO, which of course has a 1-to-1 ratio of carbon and oxygen atoms, which comparison is more useful? Meaning, what do you want in equal masses? Hopefully you say no, because we just discussed that the atoms have different masses. We would want to think about equal numbers of moles, or equal numbers of atoms. In the last 2 problems, we've used information from the periodic table. Please note, you'll always be given a periodic table. I went through 5 years of grad school. I never had memorized that thing. You get to know some after a while. Some you don't use a lot, you have to look up, but you'll always have one. So we already mentioned molar mass, the mass of 1 mole. But here they're actually bringing the definition into play from your textbook. The mass in grams, sometimes kilograms, for you it will always be grams, of 1 mole of units. Again, things. It doesn't have to be atoms. It could be molecules. It could be formula units. It could be elephants if you really wanted. A mass of a mole of elephants. That's a lot. So they have this little table here for you, and I just want to make sure that it's clear that we're still using the numbers of the periodic table. Before, they were just relative average atomic masses in AMU. Well, now, as long as we have the right number of particles, Avogadro's number, then we can use AMU for 1 atom versus 22.99 grams for 1 mole. Hopefully that part makes sense as well. Please note your textbook uses a scripted M. I will be using for molar mass. The reason for that is, maybe even today yet, another M will come into play, and it can be confusing, and in chapter 4 there's another single M, which I know can be confusing as well. So, different chapter authors choose different things. This one just chose one scripted M, and I know it can be confusing, so I'd like to make that announcement. At the bottom page, you have this image. Please note that this image does imply memorization of a process. Notice it's got little m slash big M, mass divided by molar mass, or underneath n times scripted M, meaning numbers of moles times molar mass to go back and forth. If you watch your units, you know what to do. You don't need to, per se, memorize. If you go from grams to moles, you divide by the molar mass. As long as your grams cancel out and your moles are left over, you're doing the right thing. The units tell you what to do. We're going to practice a little bit more. Notice here in carbon and oxygen, we're going from mass to numbers of atoms of that element, while in number 23, we're going to go from number of atoms of gold to mass. So just basically reverse process. We're told to use 1.0 times 10 to the 24th atoms of gold, so that's again going to be our starting point. I think I might have said 23rd. If I did, I'm sorry, 24th gold atoms. Well, the first thing we need to do is basically bundle all those atoms into the chemistry A carton, meaning we need to bundle them into a mole. To do that, we're going to use an Avogadro number. Every 1 mole of gold contains 6.022 times 10 to the 23rd gold atoms. Our atoms cancel out. We have moles. To continue to mass, because they don't ask us for the moles, no reason to stop the calculation, we need to go to the periodic table. Go to the periodic table, you find gold right under silver, and we have, what's that? Where'd it go? 196.97. The periodic table that I hand out on the max quizzes or for your exam says 197. Different periodic tables, slightly different numbers. I'm going to use the one that you're going to see most often, 197, but you can use the 196.97, I believe it was, for every 1 mole of our gold, and this will give us our mass to be 327 grams of gold. Again, we just went to the reverse. Took our atoms, we bundled them into moles, and then we used our molar mass to get the mass. Any questions? Yes?
How did you get 3 sig figs?
I put it to the 2 bits of the 1.0. No? Remember, you're not graded on stick figs per se on quizzes and exams, so I try not to over-enforce it because then some students panic. Again, I always have to have that right now. But some students I know really like the sig fig, so feel free to ask. Meaning if this was an exam question, either of those answers would be fine. And actually the one I have written down, which is 327.1, would be fine too. I wouldn't mark off because you're off in the sig figs. Any other questions? I did put number 22 onto the lecture activity list, meaning we're going to define molecular mass and orbital mass, which are defined in number 23. Molecular mass is the sum of the atomic masses in AMU in a molecule. It's the mass of that molecule, a single one, so it's particle level and it's AMU. Formula mass, as you can see, the sum of the atomic masses in AMU in a formula unit. Remember I said that we usually don't call ionic compounds molecules, and this kind of leads to 2 different definitions, slightly but they're the same thing. If we're doing something like methane and trying to find the mass of 1 CH4 unit, that would be a molecular mass. We would take 12.01 plus 4 times 1.01 and add it all together. It would would be an AMU. If we were thinking about something like silver chloride, an ionic compound, we don't really like to call them molecules, so that would be then a formula mass. It would still be AMU, and the process would be the same. You just add up the atomic masses of the elements that are present. Molar mass is the same thing, it's just on the macro scale, because we're still using the same numbers in the periodic table. So for either of them, we could do a molar mass. The difference is it's no longer particle level and be grams per mole. The mass per 1 mole. We'll still be adding up the atomic masses or molar masses from the periodic table. We're going to practice number 24. It does say molecular mass at the right-hand end of the table, but it's the exact same process if you were doing a formula mass, which you really should do for the calcium nitrate, or if you were doing molar masses for all of them. So this is tape I'm referring to. The process is going to be identical. We're going to do the first two, and then I'm going to give you the answer for the third to encourage you to practice a little bit. And there are different ways of doing this. You don't have to use a table. It actually hurts my brain, that table, but I will follow the table so I don't confuse students. So for our first one, CO2, notice element 3 is grayed out because there are only 2 elements in carbon dioxide. We're just going to think about the carbon first. We know that the atomic mass of carbon is 12.01 AMU. Well, we have one of them. That's why they have a little box number of atoms. Because of course, mass is dependent on sample size, extensive. So we're going to have 12.1 AMU contributed toward the mass of the total. That's coming from the carbon. Then we would do the oxygen. So we'll look at the periodic table. 16 AMU times, oops, I use a dot, then I use an X, times 2 would give me 32 AMU for the mass that's coming from the oxygen alone. And I'm running out of a little room on my thing, so I will go underneath. Well, the molecular mass, therefore, would be 12.01 plus 32, and that would give me 44.01 AMU. The molar mass of carbon dioxide would also be 44.01 AMU. Grams per mole, gosh. It'd be the same exact process. The units are different. My brain forgot to switch the units. So let's go ahead and do our sucrose, a little bit more complicated, adding a third element and a lot more atoms. We have C12H22O11. Well, I'm going to try to show you a little bit of how I do it. I don't like going horizontally. I like to show different ways. I like going more vertically. So for my carbon, I would have 12.01 times 12. For my hydrogen, I would have 1.01 times 22. For my oxygen, I would have 16 times 11. Well, for the carbon, this multiplication here gives me 144.12. My hydrogen multiplication ends up giving me 22.22. My oxygen multiplication step gives me 176.00 if you prefer. And then we simply add them all up to get 342.34 grams per mole. Yeah, 2 zeros on there, so we're not worried about saving. You don't have to do it in this particular layout. There's all kinds of ways, and if you were taught a different way in the past, that's fine. Just use what you use. You just need to make sure to include masses of all the atoms that are present. The answer for our calcium nitrate, its molar mass, molecular mass or molar mass, however you prefer, is 164.1. Since I did the double M, I'll say grams per mole. Or if you want to think about molecular mass or formula mass, that'd be 164.1 AMU. Are there any questions? Yes.
How about you explain what's the difference between using the AMU and using the grams on the
AMU is particle level. You're thinking of the mass of a single one of these particles. Versus molar mass, grams per mole, you're thinking of the mass of 6.022 times 10 to the 23rd of those particles. The process is identical. Yes?
How about you grams on the
AMUs of calcium nitrate is 1 unit that is not usable. If we have 164.1 grams of calcium nitrate, that is something that you can see and use. Any questions? I'm just going to put that up there. The bottom of your page is asking you to take the, actually I'll put it back up, the flow diagram we had before, but notice the word element is gone. So now we're basically thinking in terms of this flow diagram, we can think about the mass of molecules. And notice it's scripted M, so that's still macro scale. And then we can go to or from the number of moles of the molecules. And to and from the actual number of molecules. And those processes would be the same as what you're doing for an element. So for carbon, we found the moles, and then we found the number of carbon atoms. Well, this process is the same if it's a molecule. What they're asking you to add is how could you get this back down to the element level. If you know the moles of molecules, you can find the moles of an element within those molecules. And that would be using a mole ratio. For example, okay, I'm still up there. Mole ratio of carbon dioxide. For every 1 carbon dioxide unit, I have 1 carbon. Well, if I'm in the moles, I have, for every mole of carbon dioxide, I have 1 mole of carbon. For every mole of carbon dioxide, I have 2 moles of oxygen. That's supposed to be 2. And within the molecule itself, if I knew the moles of carbon, I can find the moles of oxygen, because for every 1 mole of carbon in carbon dioxide, I have 2 moles of oxygen. So I'm just trying to remind you of what's meant by a mole ratio. So you go from the molecule back to the element, meaning we can find the mass of the element by going that way, or we can find the number of atoms of that element by going the other way. If we're already in the particle level, number of molecules, we can get down to, here we go, number of atoms of the element. And then we just call it a number ratio. Here I wrote moles everywhere, but I verbalized for every 1 CO2 I have 1 carbon, right? For every 1 CO2 I have 2 oxygens, meaning 1 carbon for 1 CO2. This is a number ratio. Or 2 oxygens for every 1 CO2. Or 1 carbon for every 2 oxygen in CO2. So notice if you're the particle level, you don't have to go to the mole, down, and then back to the particle level. Any questions? I did put page 76 and 77 on the electricity list. Just some small problems. Routines, we're going to start getting really close to the end of the exam material and get back to where I was supposed to be. Percent composition. We actually have used percent composition already when we were thinking about the law of definite proportions and law of multiple proportions idea. When with definite proportions, they had 1 sample was 10 grams, and 1 sample was 5 grams, and we found out that the percents are always going to be the same, and therefore it's independent of sample size. Now we're actually going to talk about it a little more in length. So the percent by mass of each element in a compound is percent composition technically by mass, meaning percents are always partial over total times 100. Well, if we're doing percent by mass within a compound, that would be the mass of an element you're interested in. Okay, make sure I'm there. Divided by the total mass of either your compound or the sample size you're given. And of course, for a percent, we have to multiply by 100. always CH3COCH3, therefore the percent of an element within that formula can't be dependent on what unit you use. Otherwise you'd be changing the formula. Let's just make sure we're understanding. So for our sample 1, we know we have 10 grams total. We have 6.20 grams of carbon. So for our percent of carbon, we would have the 6.20 divided by the 10 times 100, and that would give us 62.0% of carbon. For sample 2, our percent carbon, our partial is 0.551 pounds. Our total is 0.889 pounds times 100. Guess what? Since acetone is always acetone, that's still going to give us the same percent. So it's not unit specific, but your numerator and denominator have that same units so they cancel out. Can it be determined from the chemical formula alone? Meaning here we are given sample sizes. What if we're not given sample sizes? We're just given the formula. Yes, it can still be determined. If so, our total sample size would be 1 mole. Using formula alone. Wow, that's bad. There we go, a little bit better. Sample size equals 1 mole. Because we have the masses for 1 mole of thing. We have the periodic table. Why would you choose different sample sizes? So if I had a mole of acetone, I would need to get that molar mass for my denominator. That would be my total. I also would need to consider the masses of all the atoms of each element present. So first for our molar mass, we have CH3COCH3. And I'm going to do it a slightly different way again. In case it's been a long time and you don't have a set way you like to do this, I like to show different ways. Well, how many carbons do we have? 3, right? 1, 2, 3. So 3 times 12.01 for our carbon. Add to that, let's see, we have 6 hydrogens. So 6 times 1.01 for the hydrogen, plus we have 1 oxygen. Do the parentheses, add them all together, and we will find the molar mass of the acetone to be 58.09. Or messy. There we go. And since I said molar mass, that's grams for every mole. So molecular mass is the A and U. So that's going to be our total, or our denominator. For our numerator, well, we already did the carbon. They don't ask us to do that. They ask us for the hydrogen and oxygen. So for our, let's do the hydrogen first, since it's listed first. Percent of hydrogen would be, for our numerator, we have 6 of that. So that would be 6 times 12.01, or 6.06 in the numerator, grams per mole. The denominator is our 58.09. Grams per mole times 100 will give us our percent of hydrogen to be 10.4. And hope that makes sense. Hydrogen is rather light. Should have a large percent. There's 2 ways we can do the oxygen. This is still the same molecule that we did the carbon up here for, right? We have the carbon up here, we have our hydrogen here, percents out of 100. If I subtract the 2% from 100, I should have our oxygen. Or, we can also do this way. Percent of oxygen would be, well, our oxygen, there was 1 of them. My numerator is 16. My denominator is still 58.09 times 100 will give me,
Move your camera.
thank you, I won't get there. I didn't want to stop in the middle because then all of a sudden I'll make more mistakes. Thank you for saying something. I was about to check, but that's okay. We give us 27.6. There's a little rounding in there. You subtract from 100, or add everything up, you're going to be really close to 100. We could save time. You know all the other elements except for 1, you just subtract from 100. Any questions? I did put number 36 up on the lecture activity list, but I'm showing you 6H6. Practice, not right now, but practice, make sure you can calculate the composition by mass of carbon in our method. And they have a little scale on there. We need to go over how to use percent composition by mass, because you're not always going to be calculating it, sometimes you'll be given it and using it. Any questions before we do that? Plus I'll have to flip my page, so I'm making sure nobody's behind. I want to have a whole page for this before I run out of room halfway through. So, in number 37, what if we're told a sample contains 44.5% sulfur by mass? What is the mass of sulfur in a 10-gram sample? We have the total sample size, we have the percent, we're looking for the partial. Percent equals partial over total times 100. Well, if we're looking for the partial, we just need to rearrange and solve for that. Partial would equal, well, we need to multiply both sides by total to put it up by our percent, and we divide both sides by 100 to get it underneath our percent. That would be the total sample size times the percent divided by 100. So our partial in this case is the mass of sulfur. Well, gamma A, mass of sulfur would equal, our total is 10 grams. Our percent is 44.5. Divided by 100, and that will give us the mass of the sulfur. It would be 4.45 grams. Any questions? In 38, they're asking us to find the total sample mass, the total, instead of the partial. We're given the partial, 2.50 grams of sodium, and we're given the percent, 39.34%. So in this particular case, we're solving for our total, multiply both sides to get it over by the percent, and then we divide both sides by the percent to get it over to the other side of the equal sign. So we would have total would equal partial times 100 divided by the percent. So our total is just total sample size, so I'll write total sample mass would equal our partial mass of 2.50 grams of sodium times 100 divided by our percent of 39.34%. And that will give us total sample size that is equal to 6.35 grams. I know this question continues with another part. Before we do that, just wait and see if there's any questions. Part A, do we know the molecular formula? We can figure it out. I'm going to write down what we already know about this sample. We know that we have 2.50 grams of sodium. We know that we have 6.35 grams total. And we're given some information in part A that's not typed on the slide. Suppose we use the figure to determine that the atom ratio of the two elements is 1 to 1. Meaning for every orange ball, there's a silver ball. We are shown a 1-to-1 ratio. On the particle level, it's 1 to 1, but also that would be on the mole level. There's 1 mole of that for every mole of the other thing. 1 mole of sodium for every mole of the other thing. If sodium is in here, is it ionic or molecular? See a metal? You should think ions, right? So this is an ionic compound because we see we don't have sodium. That will help us limit the possible other element. What's the charge on a sodium ion? +1, it's in group 1, right? Which means the other element is -1. And from the picture, we can see that this would be a monoatomic anion. What group has monoatomic anions that are -1? Halogens. So we now know that X is a halogen. Getting a little push up right about there. There we go. Well, if we find the moles of sodium, that means we know the moles of the number as mass, or as grams. Once we have the moles, then we're going to make a ratio, because our chemical formula tells us a mole ratio. So it suggests that you divide by the smallest number of moles. Once you have the mole ratio, we have to make sure it's going to fit the standards of the chemical formula, right? We can't have like decimals as our subscripts. We have to have whole atoms. So that's why it says change the integer subscript if needed. It doesn't say if needed. I said that. Next time, we'll actually go through the process, as you can see in number 43, for a sample that has a certain percentage of carbon and then percent of hydrogen. And then we're going to